Okay, let's determine how many of the following molecules are polar. To do this, we will look at the partial charges and dipoles, as well as consider the molecular geometry and how that affects the polarity. Before we start, you must know that when the dipoles will cancel out, that means that the molecule is non-polar. Alright, let's start with OF2 and drawing the Lewis structure. So first, we will draw the bond between both of the F's and the O. So then, going off of that, we know that there are 7 valence electrons in F and 7 valence electrons in this F. So 7 plus 7 is 14, plus 6 is 20. And so since there's 20, we account for the 2 here and the 2 here, so that brings it down to 16. So now we will draw the rest of them on the outside where the more electronegative element is, because it's more likely to have the electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So since we still have 4 left, we are going to draw them, or we're going to place them, should I say, on the oxygen. Alright, so that is our Lewis structure for OF2. So now, moving on from that, we will look at the partial charges. So, since fluorine is more electronegative than oxygen, it will have a slightly negative charge. Oxygen is going to have a slightly positive charge. So, the dipole runs in the direction of where the partial charge is going. So in this case, we're going to have a dipole running this way and a dipole running this way. So, now, we must use the molecular geometry that we know to determine if it is polar or not. We can't use this geometry right here because, of course, this isn't accounting for the 2 lone pairs and how that would push the 2 bonds away. So, let's draw this out in its molecular geometrical form, whatever you want to call it. I don't know how to call it. So we're going to go out here. Here's the oxygen, fluorine. Alright, then we draw the 2 lone pairs. And now we're going to draw the dipoles from before, right here, since they're going towards the fluorine. So we're going to have one right here going this way, and one right here going this way. So, this is a bent molecular geometry. It's bent clearly because the fluorines, appear to be bent. But because these 2 lone pairs are pushing the fluorines away, therefore, the dipoles cannot cancel out. And since they don't cancel out, we have determined that this molecule right here is polar. So, go over here, circle that. Oh, all right. There we go. Now, let's move on to SO3. All right. So, now, the Lewis structure is already drawn, and going off of what we learned with this one, we can determine that oxygen is more electronegative than sulfur. Therefore, the dipole moments are going to be drawn in that direction. So now, we must consider the molecular geometry for each one so that we can determine its polarity. So, let's draw the molecular geometry for this one. This one appears to be a trigonal planar. Yes, trigonal planar. And so here we go. And then draw the dipoles that we've already found. And so now, since the dipoles are all pulling equally in opposite directions like this, they are going to cancel out. And therefore, this molecule is nonpolar. So, okay, moving on to the next one. BeCl2. Okay, so let's go back to SO3. I forgot to draw the partial charges. I'm sorry. So, going back, so since the dipole is going this way, oxygen must have a slightly negative charge as compared to sulfur. So, let's draw those in. Oh, shoot. There we go. Now this is completed. All right, now for BeCl2, we know that Cl is more electronegative than beryllium. We know that because of its placement on the periodic table. So, let's give chlorine its partial negative charge. Okay, so now that we have established where the partial negative charge is and where the partial positive charge must be, now we can draw our dipoles. So, the dipoles will be pointing towards the chlorines. And now we can convert this to its molecular geometry form and find out if it's polar or not. So exciting. And so this molecule only has two domains, so it will be linear. So we can draw it just like this. Now, drawing our dipoles, it's quite clear that they cancel out perfectly. Therefore, this molecule will be nonpolar. Alright, moving on to CCl4. Okay, so this Lewis structure, again, is already drawn. And therefore, we can look at it and see, we can look at the periodic table and see that chlorine is more electronegative than carbon. So, each one of the chlorines will have a slightly negative charge. And carbon, sorry for shaking the camera, carbon is going to have a slightly positive charge. Now we can draw the dipoles. So there's going to be one in this direction, one in this direction, one in this direction, and one in this direction. Okay, let's convert this to its molecular geometry form. Now, since there are 4 bonding domains, this will be tetrahedral. So we can draw it simply like this. Oh, I'm sorry, that should be out here more. Okay. Now, we can finish with the dipole moments. So, since all the dipole moments will cancel out, as they're all pulling equally in opposite directions, this molecule right here is also going to be non-polar. Okay, moving on to the last one. Ozone. So here it has two Lewis structures because this double bond right here is constantly flipping back and forth to each side. Or it can just be found either way. I don't know. I'm not a scientist. Anyways. So, since there is no change in the here's how we are going to draw the molecular geometry for it. So that's ozone, and then here is its non-bonding pair. That is only on one of the oxygens. So, since considering the formal charges of this, and that this oxygen has a non-bonding pair, we can draw the dipole for that one like that, for this oxygen going this way, and for these oxygens going this way. So, especially since there's a non-bonding pair, and also that the dipoles do not cancel out because they are not pulling equally in opposite directions, we have determined that this molecule must be polar. So we can come up here and circle that one. Alright, so looking back, here are some common mistakes that one might make as they try to determine if a molecule is polar or not. For instance, their mistakes could start in the Lewis structure. If they miscount the valence electrons, or they violate the octet rule, then the rest of, you could mess up the molecular geometry, the dipoles could get messed up, and you have a mess. It's not going to work. Also, some kids might try to take shortcuts and memorize the amount of non-bonding domains and bonding domains, per molecular geometry term, for instance. Like, for instance, if they just try to remember that tetrahedral is four bonds and no lone pairs, then it doesn't work for that case. But aside from that, if you get the molecular geometry wrong in your head and you can't envision it, then you're not going to be able to envision how the dipoles are reacting with each other and whether the molecule is polar or non-polar or not. There we go.